a 2048 bit integer will take 6 billion years on the best supercomputer to actually factorize. And that's why we use factorization as our keys for cryptography. So all our encryption today is based on the fact that classical computers cannot break factorization. Whereas in 1994, Shor's algorithm showed that the same thing which takes 6 billion years on a classical computer will take a few hours, just a few hours, on a quantum computer. Okay, so when a quantum computer is there, which can run the Shor's algorithm for 2048 bits, for a 2048 bit integer, it's only going to take a few hours. Do we have a quantum computer that big today? We don't. When are we going to get it? Next few years. So there are several things like this. Another example that people give is caffeine molecule. Can you model molecules on computers? Well, if you wanted to model the caffeine molecule, for one of its energy configurations at a single instant, you would actually require 10 to the power 48 bits. Are we ever going to build a quantum computer, a supercomputer that big? Even if Moore's law keeps continuing for the next several years, we're not going to reach there. So hence, that's where quantum comes in, and quantum with 160 logical qubits can actually compute this for a single instance. Have we reached 160 logical qubits? Not yet. Okay.
It is very difficult to visualize how does the quantum computer will look like, because we are used to looking at the classical computer.
Yes.
So how do we envisage?
Yeah. So actually, yeah, so let me just point out how a quantum computer looks today. Okay. So the fundamental unit of computation of a quantum computer is what? Qubits. What are qubits made of? Electrons, ions, photons, several different kinds of small particles. Today, people use to make quantum computers. The one that is ahead today is called a superconducting qubit, which is basically small molecules put together. And this one, I don't know if you've seen a quantum computer today, it looks like a golden chandelier. Okay, that's the picture that most people are familiar with. At the bottom of that chandelier, it's a fridge actually. At the bottom of that fridge, it is at few millikelvins, 10 millikelvins or so. Okay. So that's where the qubits sit. As you go up, you have the microwaves, the control circuitry, which actually pass the energy to the qubits to put them into different states. So this fridge at the top is 4 Kelvin, and at 4 Kelvin is where the control circuitry is sitting. So this fridge inside which there are the qubits, the control circuitry to control those qubits, is the quantum computer. Okay, and that quantum computer is then accessed over the cloud. So you can all actually access a quantum computer today sitting here. So there are quantum computers on the cloud that you can run your programs on. So in fact, I would urge all of you today to go back. Okay, there are several ones, but the one I can point you to is called IBM Quantum. Just go there. You can create an account just like you create a Google account, whatever account you create. You can create an account and you can run a Hello World program on a quantum computer. Okay, it's very easy, very simple. Just go today, create an account. Tomorrow you'll be able to say to everyone, I ran my program on a quantum computer. Okay. Now there are several applications where people have already begun using. Okay, so there was a question from here saying, they're working in weather forecasting and things. How can I use a quantum computer? So people have actually started using quantum computers to try and solve these problems. We will come to what is the state today of how good are you at solving these problems. So we'll come to an answer to that question. But there are three classes of problems that people are solving. Number one, simulating nature. What is simulating nature? Things like molecular interactions. You have molecules, you want to know how they interact with each other. Where do molecular interactions matter? Drug discovery. They matter in things like new materials, electric vehicles, batteries, fertilizers, everywhere, rust. So one of the biggest problems in the ship and aircraft and pipeline industry is rust. So how do you reduce the rust or use materials which will reduce the amount of rust that happens? So all these are molecular interactions, and modeling that is one of the specialities of quantum computers today. The second is complex mathematics and complex data with complex structure. So how many cats do you need to see before you can recognize a cat? As humans, we require maybe 1, 2 cats. How many cats do AI systems today need? Thousands. You need a cat from this angle, from half visible, black cat, white cat, all sorts of cats, examples need to be given before cat can recognize. That the data structure of this cat problem is a higher dimensional, I mean it's a complex data, and humans, we are able to recognize cats in just 2. Classical AI today requires thousands of examples. Quantum brings it closer to human processing. Okay, so with quantum computing, you're able to model this data better and are able to extract the features better to understand what is a cat. And so today LLMs are very popular, right? Everybody uses ChatGPT. But in my office, for example, whole HR team gone, replaced by HR GPT. Marketing team gone, marketing GPT. CIO team gone, CIO GPT. But every time a new GPT comes up, what happens? A new power station comes up. Because these are very high power consuming LLMs. So we need to find better ways to model our data, learn from lesser data, and do that processing. So all of that is, it's expected that you will be able to process some of this data much better, more efficiently, in a more sustainable manner. And all of that is the second application. The third one is search and optimization. We all know what is search, we all know what is optimization. And these are getting used across different industries today, including in India. Okay, so I'm going to give you some examples of where we are already doing some of this work. So now, for advancing quantum computers, there are 3 things you require. So one is you require these processors to be able to have more number of qubits, lesser error rates, more number of gates that you can use for your computations. Why are qubits and gates important? Okay, we'll come to that. The other thing is you need software to be able to access this. Okay, so any computer today, how do we interact with it? We interact visually, right? You have a UI, you have an operating system. All of that is how you actually interact with computers. And the third one is you need error correction. So today's quantum computers are very noisy, and the noise needs to be reduced. And when I told you so there are 2 kinds of qubits. One is physical and the other is logical. Physical is the noisy qubits which we have today. The logical is error corrected ones. Okay, so so for example, today's computers, the classical ones, they are error corrected. Okay, so any computation that you run on it, that whatever results you are getting, you can replicate it again and again and again, right? So where are we today? Okay, so today this chart you don't have to understand very well, but today at least in IBM we have a 133 qubit quantum computer today. The first time error corrected qubits will show up is in the year 2029. 2029 will have 200 error corrected qubits, and The number of gates that we support today are about 5,000, but by 2029 we will be 100 million plus gates, which means you can run very, very complex programs on your quantum computers in the very near future. But until 2029, what can you do? Okay, so that's the big question. So do we sit and wait? No, we don't have to wait. Here is an example from classical computers. Classical computers, the error correction, in fact, error correction was invented only in 1950. But much before that, computers became useful. Okay, so the expectation is that we can do useful computations with quantum computers even before they reach error correction. Okay, so, and there is some evidence of that. In fact, we see it in some of the work that we are already doing. But so one of the things which happened last year was we were able to show that on quantum computers, once you reach 100 plus qubits, you have reached a place where you cannot simulate using classical computers anymore. So you are in a place where you're doing things which you cannot do with classical computers. Okay, so that's called quantum utility. Okay, so there are two definitions here. One is quantum utility, which we reached last year, where we are able to now do things on classical quantum computers which we cannot replicate on a classical computer. What are we waiting for? We are waiting for quantum advantage, where quantum advantage is where you are able to do something much, much better, much, much faster on a quantum computer than you can do on a classical computer, on a real problem. Okay, a real problem, a business problem like protein folding or maybe optimization or machine learning. In all of these areas, when you are able to do something much, much faster, much more efficiently, much better on a quantum computer, we will say that we have achieved quantum advantage. Have we achieved quantum advantage? We have not yet. Who is going to achieve it? Okay, so, PCs, we all know personal computers. Who made personal computers useful? Microsoft. Why? It gave you the operating system, it gave you tools which made it useful, and we were all, after Microsoft came, we all wanted to buy personal computers because they were useful. Who made internet useful? Two companies. One was called Netscape. Netscape built the first browser. Before that, people didn't know how to use the internet. And the second thing was Google. Google allowed us to search through all that data which was on the web. Who made AI useful? ChatGPT, yes. So before that, again, AI was sitting in the lab. It came to our laptops and our systems after ChatGPT came. In fact, today, people talk a lot about NVIDIA, but NVIDIA, before ChatGPT, was just a normal tech company. Yes, GPUs, they make GPUs. But after ChatGPT came out, their stock rose 900%. Today, they're the most valuable company, right? So same way, now, who's going to make quantum usable?
IBM.
No, not IBM. So we'll come to the answer to that, okay? So, okay, before we go there, which country has the maximum number of quantum software engineers today? China, yes. Okay, anybody for US? US, okay. Anybody for Germany? Germany. India? Okay, the surprising answer is India. Okay, so India is where we find the maximum number of quantum literate people today. Okay, so I have a global team. If I ask for somebody to be hired in the US, you know what they do? Ma'am, it's there in the news. It's
Everywhere China is such an enormous scale.
yeah, but okay. So I'll come to that answer. But yeah, so when I try to hire somebody in the US, you know what happens? They import somebody from India, give them a H-1B visa, and then they make them sit and then say, Venkat, here, I have a guy for you in the US. Okay, so the big thing now is, I asked you this question, who's going to make quantum usable? For all this talent which we have here, it has to be us, okay? It has to be India which has to do it. Okay, this is the place where all that talent is sitting, and this is where we need usable quantum advantage to come out of, okay? And so now, what are some examples of things that are already happening? I talked about quantum utility. This is a work we did with IIT Madras, where we were, doing protein folding. Why is protein folding important? Does anybody know? So the body has about 25,000 to 500,000, some different estimates people have, proteins, okay. So proteins have three-dimensional structure. So every protein has a structure. One protein can be like this, another protein can be like this. So proteins have different 3D structures, okay. So in our body, let's say a protein is like this. This protein becomes like this. Then what happens? Disease. That's disease, okay. Then what happens? Medicine comes. Medicine comes and does what? Fixes. And that's how diseases get fixed. But this medicine, let's say its shape is like this. It is supposed to fit here, but it also goes and fits other proteins in the body. What happens then? That's called side effects, yes. So today we are not able to model that. How do we do it? We go to AIIMS, 25 people with disease, 25 without disease. And then we give them that medicine. And then after that, we see, okay, what happened to you? And if there are a lot of side effects, we junk the medicine. But if the disease is big, like cancer, then we say, okay, we can live with the side effects. But that's where, we expect quantum computers in the future to come and help us, okay. Do you know what the chemistry Nobel Prize this year was for? It was for protein structure prediction using AI. So everyone knows that the physics prize was for AI, but the chemistry prize was also for AI, okay. But now, the future, okay, the future, all this personalization still cannot be modeled on these, even using the AI, the Nobel Prize. So hopefully in the next 25 years, you're going to see another Nobel Prize for somebody who actually does this on a quantum computer, okay. So there are several applications where, and this paper, this paper used 114 qubits to run this protein structure prediction. They used 300 2-qubit gates, and this was India's first utility scale experiment, which was run on a quantum computer. Of course, since then, these teams have matured, and they're going to run many more. And in the world today, there are very few that can actually do this scale of experiments, okay. And so there are two aspects to this. One is the hardware, and the other is the software, okay. So what I'm telling you today is about the software and the algorithms part. But in hardware also, we have very good things to cheer. In 1960, India made its first computer, okay. It was called the TIFRAC. It was made in Tata Institute of Fundamental Research. By then, do you know how many countries had made computers? Maybe 5, maybe 6, okay. And 2024, again TIFR made India's first quantum computer, okay. And do you know how many countries have made quantum computers so far? Again, very few, 7, 8 maybe. So the point I'm trying to make is we are very much in the game right now, okay. Especially in software, we are at par with some of the best out there in terms of talent, in terms of some of the experiments we are doing. And now, as that question here was asked, we need the algorithms people, the stakeholders who are the people who are going to use these algorithms in real life, people like pharmacists, people like, healthcare professionals, people like the weather forecasting or meteorology work that they were doing. All of these people to actually come together and solve some of these problems, okay. Because that's the only way we are going to solve these things, because As I said, in hardware, 1960 we were one of the first countries to make hardware in India, but, and also father of Pentium, Vinod Dham. But did we become a hardware nation? No, we didn't. We became a software nation, of course. Primarily because in software we had local industry come up. Local industry was TCS, Infosys, all these startups started in India, but in hardware, hardly any startups came up. Okay, semiconductors, we were ahead of TSMC at one point of time, but no local industries, so we fell behind. So in National Quantum Mission, that's why one of the primary objectives here is to ensure that not only are you, using and creating this talent, but you're also using this talent to build a local industry. And that's why you heard Dr. Funny talk about startups, talk about industry, all of that, so that we don't just export the talent, but we utilize that talent locally to build an industry here. So yeah, so I'll stop here. I think I'm running out of time. Okay, yeah, thank you so much.
So thank you, sir. So we may have a couple of questions. Any question?
Yes, Vizag.
Thank you, sir. Well, number of students are there. I think if you explain quantum computer, quantum computing, and quantum communication. Communication. Normally, I have some algorithms. Okay, if I make some software.
Yes.
Okay, computers. Okay, is work on binary logics. Okay, so I don't have to worry that whether I have to convert to 0 or 1. I don't bother.
Yes.
My like the software runs, and result is that it may slow, it may pass. Okay, so please explain that way that if anybody is interested in quantum computers, quantum computing,
Yeah.
so what are the tools? Okay, you have already told that. Okay, there is a IBM
Computer
accounts
can
they can make,
access,
and
yes,
then how whether
Sure.
it's also required some compilers or
Yeah,
That's
I'll
okay.
tell
Yeah.
that.
Please
So,
explain that.
does anybody know what language quantum computers use to program, for programming? Python, yes, it's Python. Okay, so if you know Python, sir, as you said, you don't need to learn any special, things. Just like today in the computer, you write a program and it executes itself. That's how the quantum world also programs are executed. Okay, so all you need to know is Python. There is a library called Qiskit, Qiskit, which is a library of Python. So if you know Python, which is the most popular language in the world today, if you know Python, you can use a quantum computer easily. The only difference is, for example, if you're doing bubble sort or any kind of sort on a classical computer, you would run it you'll write your algorithm in a certain way, right? On a quantum computer, you would write it in another way, where you try and exploit the properties of superposition, entanglement, and all these quantum mechanical properties. Okay, but the program itself is very simple. It's written in Python. You run it on the quantum computer, and it runs. But if you look at some of the algorithms, like I mentioned, the factorization algorithm, the classical algorithm is written in one way, the quantum algorithm is written in another way, and that's why the quantum algorithm is much, much, much faster, exponentially faster compared to the classical one.
there is some AI, quantum inspired AI. Can you explain that?
Yeah, so there are, quantum inspired algorithms also that people, run, like AI, for example. And people do this, why? Because quantum computers today, as I said, only 133 qubits, right? So if you wanted to run something bigger, what do? Okay, so what you do is you use some of the quantum principles on your classical computer, okay, and you call it quantum inspired. You're not fully using superposition and entanglement, okay? You're using some smaller properties of theirs to do your algorithm.
They are computing at normal computer.
They're computing on the normal computer. Yes.
So, anybody or any, yeah.
Do you envisage any threats to humanity or out of this quantum computing?
No, I don't. I'm very much in favor of humans ruling the world. Okay, so in terms of threat, I know people talk about threat from AI, people talk about threat from going into space, bringing, viruses and all sorts of things. But I think our human capacity is also, very, very special. At least that's what I think. And these are all tools, tools for us to aid in advancing ourselves into doing bigger and better things. Yeah, so optical also is, I mean, if you use photons, for example, right, you can do optical qubits in that fashion. But photons today are more used for quantum communications. There was this question of what is computing, what is communication. Communication, as you know, is transfer of information. So for transfer of information, photonic these photonic qubits and all are more prevalent today. For computing the property of entanglement, we are not yet able to do it very well on using photons.
You just share that in terms of data sets, AI algorithm robustness is decided upon the how many data sets you have. But the quantum technology mimics more of like a human, lesser data points. But at the same time, it is said that in terms of encryption, it is much more secure. It leads to better security. How is it possible? Like with lesser data points, at the same time, you are ensuring much more secured kind of data.
Yeah, no, the security is not coming from having more data. It is actually coming from the property of that qubit, that if you are observing it, if somebody intercepts it, you will come to know. Okay, that's the property you are actually using to do the encryption, the quantum key distribution. I think the others after me will talk more about that. But yeah, so, right.
Okay. Yeah. I
Okay,
think we
thanks a
can
lot.
take this last question. One more question.
yes.
Yeah.
Hello. Good afternoon, Venkat. Your class were very inspiring and positive. So I'm Cyril from Visvesvaraya Industrial Technological Museum as a curator. So we are in the science communication. So how can we explain to a common man how a qubit can do faster communication or more computations compared to a bit? And how can we explain a quantum computer to a layman?
Yeah. So actually today, if you see, a lot of the lab level, room temperature kind of things are shown using light. Okay, single photons and things. So for a museum, I think it will be ideal to show how that photon is able to get into multiple states, the superposition, entanglement, all of those experiments, which I think in school also we do, or was it in college, somewhere we did those single slit, double slit kind of experiments. They show the properties, okay, of the quantum mechanical particles, the qubits. But in terms of speed, okay, I'll have to think, okay, I don't know how we can show it using maybe 2 qubits or something. Maybe somebody else has a better thought around that. Yeah.
I just
Thanks.
want to know that qubits means it will change its state continuously, right? Then how can we attain accuracy for a particular program we are giving?
Yeah, okay, so for example, there is something called coherence time, okay, which is for how long does the qubit remain in that state which you put it in, okay. And you're right, it remains there for, at least in the computation world, the qubits we use for the computation, they remain for a few milliseconds only, okay. So any computation that you do today has to be done within that window of time, okay, because otherwise you're going to lose that state, okay. So those are the things which are, the research issues, and the National Quantum Mission is also addressing a lot of these issues. And yeah, so I think the speakers after me will be more, they'll tell you a little bit more about some of these things. Yeah, thanks. Yeah.
So thank you, sir, for your thought-provoking in this keynote address and giving industry perspectives as well as the current status of the R&D for developing quantum computers in the world. So now we'll move to the plenary talks. So the first plenary talk is by Professor Bhaskar from IIT Delhi on quantum communication technologies, status and challenges. Professor Bhaskar is working as IHFC Chair Professor at Department of Physics and a joint faculty at Optics and Photonics Center, IIT Delhi. Prior joining IIT, he was a postdoctoral fellow at Institut TQ France and earlier at Max Planck Institute for the Science of Light, Germany. He received his PhD from University of Delhi and National Physical Laboratory, New Delhi. His research interests are in optics and photonics, quantum optics, quantum entanglement, photonics technologies. He has published more than 70 research papers in peer-reviewed international journals and about 130 conference presentations and invited lectures to his credit. He has been awarded Teaching Excellence Award 2022 and Veena Arora Early Career Research Award 2022 by IIT Delhi for his teaching and research contributions. In 2023, he has been selected as a member of the National Academy of Sciences India and Indian National Academy Associate Fellow. Some of his notable contributions in fiber-based secure quantum communication are the Intercity Quantum Secure Communication for 100 km in 2022 and the Trusted Node-Free Quantum Secure Communication for 380 km achieved in 2023. Currently, he is pioneering research in quantum communication technologies at IIT Delhi under National Quantum Mission. He is the lead PI in quantum communication vertical and leading a technical group on hybrid quantum communication network. So we welcome you, sir. Please.
So thank you.
So let us welcome the speaker.
So thank you very much for the kind introduction. So can you hear me in the back? Yeah, thank you. So first of all, I would like to thank IISF organizers for giving this invitation and giving this platform to discuss some of our recent activities in quantum communication technologies. So the goal is to give you some ideas on what quantum communication technologies are, what is the status, what we are doing, what are the challenges we are facing, and what could be the roadmap for the Viksit Bharat at the rate 2047. So the first question which comes is that what is the motivation behind jumping to quantum technologies? And all of you must agree that the new era which is coming now is what we call the quantum era. And if you look back to the technologies, the way they have progressed, in the last century there has been strong impetus toward understanding quantum science because the goal of the technologies was to miniaturize, and once you keep miniaturizing things, essentially you will lead to the state where you will approach the Planck constant, which is the smallest possible number, to realize. And to go toward that direction, the classical principles or classical physics is not going to work, and you have to invariably come up with the quantum principles, or you have to use those quantum principles. So this is one of the strong motivation that one has to use quantum principles for the technologies. The second one is the promise which is offered by these new kind of technologies which are based on quantum science. And over the last decade, we must have seen several such technologies which are shown in the below side. Quantum computing, for which already a talk was there. We have quantum sensing and metrology, where the goal is to make sensors which are way better than the classical sensor using quantum technologies. And in fact, the example is the Laser Interferometer Gravitational Wave Observatory, LIGO, which is detecting gravitational waves for last 10 years. And very recently, they have come up with what we call squeeze light or quantum light to introduce it so that the noise has been suppressed, and it is 2 to 3 times more sensitive. So what we can expect is many more astrophysical events in the near future. As already mentioned, that quantum computing is essentially going to give you a technology which is orders of magnitude better computational capability, and that is going to be a threat for the existing security solutions, and one needs to come up with a new way to secure those solutions or the communication, and for which this quantum key distribution is used, which essentially works on the principle of quantum physics. I will come to the later what exactly it is. However, the China has been a leading player here, which has demonstrated satellite-based quantum communication for more than 1,500 kilometers. And essentially nowadays the goal is to shift from quantum mechanics to a quantum engineering. So many of you must have come across these two news over the last month. The first one is the harvest now, decrypt later, why hackers are waiting for quantum computing. So what essentially is being done is that the existing cryptos or codes are being stored and they will be used once a quantum computer comes up so that they can be broken very, very fast, and then the keys can be used to steal the information. Or even China hacks a military-grade encryption using quantum computer, poses threat to the West. And that news was essentially came up as a hype because what they used was a 50-bit number, which was actually not requiring any quantum computer to break. However, these are the news which are in the public domain. And if you look into the classified side, there may be many more things which are happening, but which are not actually coming to us. So what essentially it means that quantum securities are the need of the hour, and we have to go for that. There are many ways by which you can do quantum key distribution or quantum communication. One is what we call the free space or satellite-based method, where we can either use a line of sight kind of structure or even a satellite, where a satellite is somewhere sitting at the top as a trusted node. One can have two ground stations and they can communicate between the ground station, they can set up the key. And China has demonstrated it up to 2,000 kilometers. In fact, there are not only this, but many other ways satellites are being sent in order to do QKD, which is either in the form of small satellites, which we call CubeSats, or even nanosats, or even geostationary satellites. And there are plans to make satellite constellations by which the QKD can be put all over the globe. So these are the ways for intercontinental QKD networks. However, one would also like to reach every house, so that means local networks. And for that, fiber is the best choice. If you look into the current state of art, the first hybrid network was developed by Tokyo in 2010. And China has already come up very, very aggressively in this direction, and currently they have a backbone network which is more than 5,000 kilometers, even connecting their satellite ground stations. And this essentially tells us that there is a need of multi-node quantum networks which are compatible with existing communication architecture. For example, the fibers which we are using for internet at the moment. In fact, if you look into quantum communication technologies, there are myriad of applications of these technologies. They are not just limited to encryption or randomness or maybe some of these areas, but in fact they are connected closely with sensing and computing, because if we are thinking of a big network, then we can have many, many sensors placed in different places, quantum sensors, and we need to connect them with some server using some secure communication network. Similarly, computers may not be at one places, but they are distributed over different places, and we again need to connect them using the secure communication or even quantum internet. One can do quantum teleportation, that means one can send the quantum bit from one place to another very, very quickly, and also can be having applications such as clock synchronization. In fact, this is the area where the market has been projected differently by different people. Quantum cybersecurity is a very, very broad area, and in fact there are some projections that the market value is more than US 20 billion by 2030. And there are many, many users of quantum communication systems, which include not only governments, but also the strategic forces such as military, telecom, and data centers, as well as the banking or financial sectors, including mobiles. So this is the area where, so with this I would like to briefly tell what I am going to give you an idea for next 15 to 20 minutes. So I'll briefly discuss technically what QKD is, what is its need, why it is essential. We have done several activities in this direction for last 4 or 5 years. So I will briefly give you the glimpse of activities what we have been doing in developing these technologies. I will discuss what is entanglement and how it is going to be used in communication. What are the challenges associated with them, and what could be the road for Viksit Bharat 2047, and what are quantum networks and how it is connected with QKD. Okay, so essentially QKD is a form of technology which is going to use, in our case, photons for setting up the keys, basically generating and distributing the keys between the authorized parties. So we have two parties, for example, Alice and Bob. We use a quantum channel where we send our quantum particles. In our case, these are photons because the speed of photon is the maximum, that is the speed of light. We use these photonic qubits with some degree of freedom so that we could encode the information. That could be either polarization, that means we can have horizontal polarized photon, vertical, or even their superposition. We can have orbital angular momentum, or we can even have time bins like early arrival or late arrival of photons. And by that, we encode our qubits, we send from one to another, or from some central resource to both of them, and then using the classical channel, we set up the key. In fact, the goal here is to use the existing fiber infrastructure, that means off-the-shelf components, and two types of strategies one can use. One is called the prepare and measure strategy, and the other one is called the entanglement-based strategy. So in the first one, the Alice is the sender, transmitter, Bob is the receiver, so Alice prepares some quantum state, some photons, sends to Bob, Bob makes a measurement, gives some information about the measurement to Alice, and then they set up the key. In the entanglement-based case, there is an entangled photon source which is somewhere sitting in the middle. One photon out of it sent to Alice, one to the Bob, that means Alice and Bob both are the receivers, and then they set up the key. If you look into the comparison between them, there are several benefits in each of them. For example, the rates can be very, very high in case of prepare and measure QKD because one can use sources such as weak coherent pulse sources where the rates can be really very high, megahertz or even more. In case of entanglement, the distances can be longer because we are sending photon from the center to each direction, so the distance is easily twice or even more. However, if you look into the security, the entanglement provides you an extra layer of security. That means that even the source itself can be with the hacker, but still it can generate the keys which are the real keys. That means which are not compromised, which is not in case of the prepare and measure. And also one can make what we call trusted node-free networks. So trusted nodes are something like that. Suppose I can make a QKD for 50 kilometers. Now if I want to go for 200 kilometers, I have to make those stretches of 50 each, and I have to connect somewhere in between with some user, which we call trusted node, which are the weak security points, and one can actually attack there. So the ultimate goal is to make a trusted node-free communication where nothing of this sort is there, so that everything is fully safe. And entanglement has a possibility to provide that with the help of many technologies such as repeaters, and that is fully compatible with these kind of technologies. So now I will give you an example of each of those methods, what we have been doing. So the first one is what we call differential phase shift or DPS QKD, where the left side is the preparation stage where we use a laser beam, we attenuate the laser beam to very, very strongly so that we have very less photons in each of the pulses. We randomly provide phases to these pulses and send to the receiver Bob. Bob has an interferometer, basically we are talking about optics. Interferometer which is a 1-bit delay interferometer where it interferes with the other pulse and gives the output in the detectors 1 and 2. Depending on the phases here consecutively, we can get either 0 phase or pi phase, and accordingly different detectors click. Now the timing of these clicks can be noted by Bob, and they can be shared with Alice, where looking into those timings, Alice also knows what was the phases. So basically both have the information about the difference of phase, and that way they can set up the key. And this kind of protocol is very useful for fiber-based quantum communication. So we did this a couple of years back in our lab first to show that we can have that competency in terms of long distances. So we go for 110 kilometer fiber spool in the lab. These are the fiber bundles which can be used for testing. And we have shown a key rate of about 15 kilobits per second with an error which is we measure in the name of QBER, QBER, that tells you that how many % of the photons were reaching wrongly. And that number should be below some threshold, which should be typically 8 to 10% depending on the protocol. So we could go up to a lower number than that threshold. Then we took our system to the field. So essentially our transmitter was at Prayagraj, and we took a underground fiber of 100 kilometers connecting the nearby city called Vindhyanchal, where the receiver was kept, and we made a QKD between these two cities using the fiber which was already laid with a loss of about 26 dB, and we found a rate of about 10 kilohertz and a QBAR of less than 9%. So this was the first long distance QKD which was done with the help of DRDO and IIT Delhi in India. And in fact, we could have gone even more, but the fiber which was available was only 100 kilometers, so we were limited to that length. Then we asked the question whether this is the maximum distance or can we do better, because the longer we can go, the less number of trusted nodes we need to put in between. So we looked into, as a research site, that what could be their contributions coming from different components we are using in our quantum bit error rate. And we found that not only the Alexander, but also the dispersion in the fiber, the medium dispersion, as well as the counts of the dark counts of the detector are the main culprits which are adding to this noise. So we tried to minimize each of them independently, and we then tried our experiment again, this time with more refined version. We started with 2.5 gigahertz pulses. We use a dispersion compensating fiber which reduces the dispersion. We use superconducting nanowire single photon detectors, which are a very latest technology and which has very low dark counts. And we took everything, synchronized it with an FPGA. So you could see that it not only uses optics, it uses a lot of electronics, a lot of computing. So it is a multidisciplinary area where QKD requires in order to develop such technologies. And with this, we could test our setup. So when we work at very high detection efficiency of our detectors, we could go up to 265 kilometers with an error of less than 2.4%. However, our detectors allow us to work on different operating points. So we operated at around 1 count per second error noise, and in that case, our QBAR was less than 1.5%, and we could go up to 380 kilometers in the lab. So this was, in fact, a very stable system with fluctuations less than 5% in 5 hours duration. So essentially, if we compare our demonstration with whatever has been done over the globe, you could see that this is the longest distance QKD using the DPS protocol with an error of less than 1.5% and with a distance of 380 kilometers. And it clearly reduces the dependence of trusted nodes. So up to 380 kilometers, essentially we don't need anything to put in between. So this was one type of protocol which we worked with. Now I will come to the other type of protocols which require quantum entanglement. So as I told you that entanglement or quantum properties cannot be a limiting case of a classical feature. So lasers or any other devices attenuated up to certain level may not give you the entanglement kind of features, and we have to really generate entanglement with some quantum phenomena. So we use a specific phenomena which we call spontaneous parametric down conversion. Not going much technical details, essentially we are shining a laser with a nonlinear crystal, and it is probabilistically giving you some photons which are correlated quantum mechanically. So you can get these kind of rings which you can measure with some single photon sensitive camera, and you could see that these rings are those places where photons are correlated. In fact, you can get a particular case where there are two rings which are crossing each other, and these are the crossing positions where you can find quantum entanglement. Now, in fact, quantum entanglement is something which was proposed quite early, somewhere in 1930s. However, it was not understood much at that time, but later on, after John Bell and other theoretical researchers, there were proposals how to test it, and these were the three gentlemen who not only generated and tested it, but also shown many applications of quantum entanglement, and they have been awarded the Nobel Prize of Physics in 2022 for their contributions. So essentially, this entanglement itself is a property where the generated particles individually are completely indefinite state until they are measured, but if you measure one of them, you immediately know about the other. So an example I'm going to give you about a particular state which is we call as a Bell state, where there are photons having different polarizations as horizontal H and vertical V. Suppose you have a source like that which is giving these photons, and you take these two photons away from each other, let us say in different galaxies. So So the distance doesn't matter. Wherever they are, they can be anywhere as possible. Now if you make a measurement in one of them, let us say you measure its polarization and it comes horizontal, you immediately know that the other one is in an orthogonal polarization, that means in the vertical. And if in the next measurement you measure it in orthogonal polarization or in V, then you immediately know that its counterpart is in H. So this is something which is not possible with classical means, and this can also be used for communication applications. So for example, we have made several sources which can generate entanglement in the lab. We can measure entanglement with a property called Bell violation, and its value should be more than 2 and limited by 2.81. And you could see that all these values are toward 2.8, that means the entanglement quality is very good. The last one uses a all fiber kind of source where there is no free space involved. And you can use this for distribution of entanglement using fibers. For example, we take that entangled photon source in the center, we send one photon to one direction through fiber, the other one through other direction in the fiber, and then make the measurement. And after the distance traveled, if we measure again the Bell parameter and again comes more than 2, we know that the entanglement has survived to that distance. So you can see that up to 50 kilometers, the value has not deteriorated much from 2.6. Then we can do a quantum key distribution with entanglement, and you could see that we have a key rate of about 1.4 kilobits per second with a Q-bar of 2.77. So essentially this tells that the quantum entanglement based QKD is possible in the lab. We took the one photon now around the IIT Delhi campus. There was an underground fiber which was about 8 kilometers. The other side we took another fiber of 10 kilometers, and we have shown that for up to 18 kilometers also, which includes the field deployed telecom grade fiber, we had a key rate which was about 2 kilobits per second with a Q-bar of less than 3%, which opens the door of field demonstration as well as deployment of these kind of QKD sources which are based on entanglement. That means that they have an extra layer of security. Now the question comes, what are the open challenges? 2-3 minutes. Perfect. What are the open challenges? So there are challenges associated with the securities, because essentially QKD is secure as a theoretical point if your experimental setup exactly resembles with the theoretical speculations. But if your assumptions are different than the experimental realized system, then you have to test it for the security. The goal of getting rid of trusted nodes and use of repeaters in one of the area which is still being explored. The cost is one of the very, very important area, and currently the costs are really very high, and one needs to load down them as much as possible. In fact, one way to do that would be to communicate both classical and quantum signals through the same fiber, so that the number of fibers could be reduced. And we have recently shown that that is also possible, and up to 50 kilometers in our case, we could still communicate with both classical and quantum signals using the same fiber. And that tells us that the cost can be reduced significantly. So before I close, I would just like to give you 1 or 2 slides about what is the expected roadmap towards the quantum internet. Already Venkat mentioned about the computers. So that if you look into the existing classical internet, you see that in 1950s we had the first computers, then there were transistors and ICs after 10 years, and subsequently in every 10 years we have development in the Ethernet, the Mac systems came up, and finally in 90s we had the internet, which we use nowadays as well. In a similar fashion, if you look into the quantum area, we have the D-Wave kind of systems in 2010 onwards. We have quantum hardwares and supremacies where we are currently living in. We have multi-node QKD networks which are expected in next 5-10 years. And then in the next 30s, we expect to have a full stack quantum computer. And once those computers are available, we can have the quantum internet by connecting those systems, which will be well before the 2047 target. That means we can have a very nice network with quantum features before 2047. I would also like to mention that under this National Quantum Mission, we are working on a project which is named as Towards Trusted Node Free Quantum Hybrid Quantum Secure Communication Network, and in short we call it Tehqiqat, which essentially means to explore and to investigate. So we are going to set up a network of about 300 kilometers connecting 4 states, that is UP, Delhi, Haryana and Uttarakhand, connecting several educational institutes, which will offer us a way to play about entanglement-based networks, non-entanglement-based QKD networks, and all kind of devices development up to TRL 6 to 8 levels. And this will be a way forward for quantum internet. In fact, one of the requirements in developing deployable devices is to have integrated devices. That's why we are often calling about manufacturing hub. And in case of QKD, already such devices have been developed with paper and measure systems. And in our proposal, we are also aiming to have integrated solutions based on entanglement. And we hope that by developing them, the deployable QKD systems would be a possibility, and a QKD networks and quantum internet would be soon realizable. So I would like to summarize that we started with quantum revolution and quantum technologies. We showed some of the developed QKD systems as well as their uses, and also emphasize the need of QKD networks. So I would like to thank our group and the funding agencies for their cooperation. So thank you very much.
Yeah. So in the interest of time, directly we'll go to second talk. We can have question answer during the panel discussion, as the speakers will be part of the panel discussion as well.
Thank you.
Yeah. Yeah. So thank you very much, sir, for your detailed talk and explaining the fundamentals and the differences. Thank you.
Thank you.
So let us thank the speaker with the Yeah, so this is the second plenary talk on cybersecurity perspectives in emerging technologies, that is AI, quantum, and 5G, 6G. And the speaker is Dr. Sirdhar CV. He heads the Quantum Technology Incubation Group at TCS Research. In this role, he is responsible for building capabilities around quantum computing, quantum security, and sensing. Leading a team of researchers and young scientists, he works closely with the national and international ecosystem. He is the member of the Code Quantum Task Force representing India. He is a member of the DST Expert Committee under the National Quantum Mission. Dr. Sirdhar works closely with the Indian Academia, TIFR, CSIR Labs, CDAC, CDOT, and quantum technology OEMs and startups. He has 3 patents in quantum computing. Prior to this role, he led initiatives such as AI engineering, UAVs and drones, and the Intel Center of Excellence for IoTs. Currently, he is the Vice Chair for the Telecom Security Group at the Telecom Standards Development Society of India and a member of ITU National Working Group 13 for Future Networks. He is an active speaker on emerging technology topics at various universities, incubators, and in IEEE conferences and different platforms. He holds BTech in Electronics and Communication and postgraduate diploma in Strategic Management from IIM Indore. We welcome you, sir, for this talk.
Thank
Yeah.
you. Thank you, everyone. And, good afternoon. Since the title of the talk is not just quantum, it has got AI and communications as well. So I thought of extending the topic beyond quantum and cover some of the things that we are doing and highlight some interesting aspects. So you have some interesting pointers from our research. With that, I'll just get into this one. So one slide, a couple of slides I want to talk about TCS. So all of you know TCS, which is India's largest IT organization. So we are a $30 billion organization with more than 600,000 people. So you can imagine 600,000 people building a software for a 600,000 people company itself is an activity. So so it is driven by very, very interesting systems. Just imagine the cybersecurity aspects of the 600,000 people. So people can easily leak information, and we need to do a lot of internal security controls, etc. So many things. Right? But the point is, as TCS, so we also invest a lot of money in research. So we spend about 1% of the revenues, which is about $330 million in research. It's like 2,400 crores research and look at all the futuristic technologies that are coming. So the research at TCS itself is a case study at Harvard Business School. So we are organized in a very interesting way. So we have the team is split into two parts. So the first part is research, so what TCS should do beyond 10 plus years, and the second part is the innovation, what TCS should do in the near term. So slightly reorganizing this into as the future of technologies and the tech explorations kind of model, where the future of X is something that we work on sciences. So these are all different kinds of sciences that we are placing bets on, so which will translate into innovations later. Working in silos will not help, so we also need support from multiple stakeholders, and that is the reason why we created something called Co-Innovation Network. And I also had the Co-Innovation Network for the academia, so it's an industry academia research network. So here we work with academia, so startups. So we partner with about 3,000 startups to work with accelerators and VCs and multiple alliance industry forums, etc. And build all these emerging technologies, and we have to show this to our customers and our stakeholders. So for that, we created something called Spaceport, which is the innovation center. So these are multiple innovation centers that exist across the globe, and this is where we showcase all the innovation. So anything that we build will be demonstrated at all these innovations, and these innovation centers are also open for academia, startups. They can also come and work along with us. So we have a rich patent portfolio, so we have about 5,500 researchers working in different business groups, about 68 academic partners, so we work very closely with multiple universities, fund a lot of research programs. We have a very interesting research scholar programs also, which is run by TCS. So just in the interest of time, I'm skipping this slide, but this is our co-innovation network. So we work in almost all the best universities across the world. Coming to the topic, so I think we heard a lot about the quantum computing from Venkat sir, and then Mr. Bhaskar sir, we talked about the QKD part. So I'm going to extend the same things on what TCS is doing and what TCS is tracking, and based on that, I'll try to see what are the things that are coming and maybe leave you with some thoughts. There are also many risks that are coming. I think somebody has already asked the question around what are the risks these technologies can create. So I'll also highlight upon some of those aspects. So the first part. So let's take a look at the technology roadmap. So if we try to map all the three things in the same slide, right? So we have the quantum technology, so which is say the green line, and we have the classical computing, so which is the computers that we are using on the blue line. We see an inflection listed around 2027, so probably will argue that the utility regime is already there with 100 plus qubits from IBM. So IBM has announced a 156 qubit quantum machine last couple of weeks back, which has got more than 5,000 gates. So looking at all these things, we are at a state where we will never be able to simulate quantum power with the total classical computing that exists with us today. So that's the scenario, and IBM and Google, they're given the roadmaps for 2030 with a million qubit roadmap, and it is shaping up very well. The reason for it is also mainly because of the amount of funding that is coming into it, so which is about $50 billion plus is getting invested into quantum, and it is a national program for more than 24 countries, and India is also investing $1 billion into this one. So with all those things, quantum is shaping up very well. At the same time, the classical computing is also shaping up very well. So I'll just come to that shortly. But if you look at the measurement of this one on a nanometer scale, so we're looking at reducing to these 2 nanometer technologies, which we see right now coming from PMSC. So we're able to package more number of transistors per chip. And so we will be doing this, the TSMC will have 1.4 nanometer in 2029. So this classical technology is also moving very fast. So which means it will challenge the quantum. So whatever we can do in quantum can in some way simulated in classical for some time. So we'll not be able to do in the long run, but you can do it for some time. And now if we map even the another technology 5G onto this one, so that's when the story also becomes interesting. Because now when you bring connectivity aspect to it, you have a lot of flexibility to add where you want to store the data, where you want to move the data and all those things. Right? And India is already discussing about 6G, so the Bharat Alliance, Bharat 6G Alliance. It is also set to come around 2030. So with quantum coming around 2030, 6G coming around 2030, say let's say even the classical computing also beating all the limits by 2030 and supporting AI. We are looking at 3-4 technologies that are coming together, which actually creates a very nice inflection point always. Right? So we've seen in the past, so like with 4G, we've seen we started using videos. Before we were only happy with messages. So now probably we will also be seeing virtual reality. So a lot of interesting things are possible. With 6G, we also have many more interesting things coming up. So which will be the sensing integrated into the antennas itself. So you can do the environment scanning and all those things. Those things are possible. And then the terahertz communication. So we'll also have some more interesting aspects here. Right, so yeah, just moving forward. So because there was a question around how this quantum computers will look like and what is the state, I just pulled up 2 slides quickly from my old decks. So these are some of the quantum machines that are available today. We have an IBM version, so which is 1121 is an old number, but now you can say even a better version of this one is 156 qubits. Google is working on stealth mode with their quantum machine, and we have Ligeti, which is another superconducting-based quantum machine. So we have IonQ quantum machine, which is a trapped ion-based technology under it. Then we have a neutral atom-based technology, quantum computer, and then finally we have a D-Wave, which is an annealer. So these are different kinds of quantum machines. So for visualization, I think, but more than that, I think Venkat has explained how this will look like a chandelier, right? So you have a quantum processor, and on top of it you have good amount of cryogenics. All these things bundled with huge amount of electronics, right? So that's the reason why Professor Bhaskar mentioned about the multidisciplinary nature of the subject. And you need to understand cryogenics, you need to understand getting the superconducting states with materials, and then also you need to have good knowledge of electronics to realize a quantum computer. So it's again a multidisciplinary subject truly. So now let's take a look at the classical computing. So this is something that we are tracking. So we are already comfortable with a lot of Intel, NVIDIA systems that are already available. But there are also other players who've been building these technologies which are used in very specific instruments, like all our mobiles have got processors from ARM, or automotive cars will have processors from NXP, etc. All these people are actually making processors from long time. Right? And then we also have a set of players who are making these high-speed electronics, which actually go into these quantum machines. And Professor Bhaskar again mentioned about the FPGAs. So these are the companies that are supplying them. So these bottom 2 blocks are already there, but there are some very interesting things that are happening over the last few years. So we are getting these new processors from AWS, Google, Microsoft. They're building their own processors to accelerate the data center traffic or the data center use cases. But they're also coming at the technology level equivalent to Intel, AMD, and others. And they're using the same fabs to generate these processors. So which means you are seeing a new set of companies that are building these processors, which are used in data centers, and these are also accessible by us, right? You cannot access them through cloud. But there's also another interesting trend that is happening. Now people said, okay, fine, so we are hitting the limits. NVIDIA is also not sufficient for me to run my AI models. So I'm actually stepping ahead and then creating a new generation processor by combining multiple processors, increasing the density, and then building very specific architectures for accelerating specific AI things. Right? So you will see a set of startups who are actually, these startups are doing very well, and most likely I think we will see a scenario where either these guys will lead them or they will lead these guys. And already we have heard some news like Intel is in trouble and they're for acquisition by Qualcomm, so such kind of news we have already seen, right? So why not one of the startups acquire Intel itself? So a possible scenario, right? So now you have two scenarios. One, you have quantum, so which is shaping up very well. Then here the classical computing, which is shaping up very well. And the third, there is a scenario of communications, which we are also, it's also shaping up very well, and we'll be reaching gigabit speeds with 5G and 6G. So all these three things are giving enormous power for us. So which means we will combine all these things and do. So we can reimagine our data center infrastructures for research. If you want to make an investment for your research, you want to build a big data center, say for 2028. With these trends, do you really want to make that investment and then say it will sustain for long term? So that's a question that we have to ask ourselves, right? So that actually puts us in a kind of dilemma. So these are all the best parts of it. Now let's look at some of the risks that these technologies are also creating. So yeah, Dr. Venkat talked about most of these applications. So if there is a single quantum computer, so it can solve problems related to AML, simulations, and these are 4 areas that we also work at PCS, right? So, but the point is, right now with one quantum computer, so you have sufficient power to break the prime factorization problem, so which means we are getting into trouble with the RSA algorithm, so which is no longer safe and secure. So we have already the theoretical foundations are established that, okay, so if you have a decently powerful quantum machine, so you can break this. But we are not talking about a single quantum machine. So there can be a scenario where a group of small quantum machines come together and become big and act more dangerous. So that is even more dangerous scenario, right? And then we have this harvest now and decrypt scenario. So people are now storing the data so that in future we can get ourselves protected. But luckily, so yeah, people are also thinking about this risk, and then NIST has already announced some standards for this one in the month of August. So now organizations are looking towards moving towards new encryption schemes so that you can protect from the harvest and decrypt now attacks in future. And last week there is a report from NIST, so it is an internal report, so which has already deprecated this 112 bits of RSA after 2030. And they have actually given a series of deprecation of algorithms. So which means we are already in that scenario, right? Our existing encryption schemes are at risk by quantum machines, so we have to do a lot of work to lift all our existing applications into the new things. So what we need to do, so organizations are already working on it, so we are already working with multiple institutions like banks, etc., in terms of identifying what is the risk of this one and how I change their application. So each of these big customers of ours have about 1,000+ applications, IT applications. So now I need to understand the risk of all these applications and migrate them into the new encryption schemes. So that's an activity that we take up. So but this is there's a framework that is happening, good amount of jobs that are going to come in this area, so this is a near-term thing. So an opportunity that is getting created. Now let's look at the cyber security part. So we talked about quantum, so now let's move to cyber security a little bit. So here also, so I think all of us know AI, so most of us have started using it, knowingly or unknowingly, ChatGPT. But what we see is this AI is more or less like a black box. So typically algorithmic world, so you know what is the input, what is the output, so you'll be able to do with some mathematical functions and all those things. But when you add probability into it, so that when the thing becomes a little complex, and then you get into a scenario of the black box problems, right? So if you have an image where you want to fire a missile to kill one person in that crowd, and you are using AI algorithm, so will you make a decision on that one or not? So the question is, well, the technology is powerful, but still there is no answer for this one which creates a risk, right? So typically in a traditional world, so we have these data sets, we do pre-processing, feature engineering, and then training, and then we are doing the inferencing, and we're getting the output, right? But there are so many questions that are out there which we don't know, we don't have the answers to. So how do we solve these problems, right? So if you go to a bank and bank rejects a loan based on some AI algorithm, and then bank says my machine has told me that the loan is rejected, right? So now you have to ask the question. So on what basis it is rejected? So in an algorithmic world, it is very clear to tell, right? So these parameters are considered in my equation, so it is rejected. But in case of AI, so the answer is very difficult. And now when you challenge them in the court, so now the lawyer should also understand, the judge should also understand that this algorithm should be explained, right? So Uber had got one such case. So when they use search pricing, so they had to go and defend in the court, right? So but how do you make this safe? So this is also not safe actually. So you have to make this safe. So what we need to do is there are multiple things that we need to add to this one to make it safe. So the first one is the data itself, which is the problem. So you have to make it safe. So there are methodologies that are available. So to make this to build these AI models in a safe way. But that is also not enough. There can be bias that can be introduced during this pre-processing stage where you do a wrong selection of things for building the models. So that can create another set of problems, right? And more than that, so you need to have the explainability of this model, and it should have the guardrails so that you can question, when you question all these things, so you can talk about the data, you can talk about the bias, and you can also explain your algorithm. So there are tools that are there which will help you to list your AI algorithms and then explain for both the data categories as well as the image categories. So and more importantly, not only this actually, you need to maintain these models, the repository of these models, which is a huge expense for any company, right? Whenever you retrain these models for new data sets, you again have to store these models because that Uber case, if 4 tasks and say that my model is already gone, so you have to reproduce the same model, explain how the decision was made and all those things. So this is going to create a huge amount of opportunity. The regulations are still evolving. So in the Europe, it is the Europe AI Act that has come into play. Whereas in other countries, the regulation is very flexible. Nobody is even worried about what will happen. But this can create significant risk, and hence there's more opportunity. Luckily, there are also frameworks that are getting developed around this one. So we have the NIST framework that is available to build your AI models. So the point is, some of you might be working on building this AI technologies, so you should consider these guardrails initially itself so that we don't regret later. Apart from this, so the cyber attacks on AI models is another separate topic by itself. So we talked about the risks of the AI model itself, then now the cyber part of it. So the OWASP, which is a standard community that reports risks around AI. So it has listed the 10 different types of attacks that are possible. So these are scenarios that are possible when you get into better networks. So what happens if somebody steals your model? So you put a lot of effort, created a ChatGPT model on a huge amount of infrastructure, and then you deployed it somewhere, so somebody has actually taken that model, right? So those kind of things are definitely possible. And some of them, you can attack the model and just get the response, do a DDoS, and then create all the scenarios, whatever the model is giving, and then replicate all the scenarios and use it as an AI model. So all your investments are gone for toss. So this is another area that should consider. So the principles for this one is mainly, so there are a couple of frameworks that are getting popular, so which should be considered in while building these technologies. So the NIST AI risk management framework that questions all these risks that are coming from the AI and then helps you to build these models. And there's also ISO 42001, so which is a standard, so which can be used for building the AI models. So the last area is about the 5G and 6G. So this is again another huge topic, but I'll just keep it very simple. So typically, in our conventional networks, so we've been taking devices from Nokia, Ericsson, and all these companies and build our radio networks. But what has started happening with 4G and towards in 5G is except the radio unit. So the rest of it is all built on an open architecture, which means you can open your laptop, install a software, and actually create a 5G core network, and also a part of the 5G RAN network. You can integrate with an antenna, and you can actually deploy a 5G network. So all these are open source, available, and anybody can do it. So, but in commercial grade, so we use cloud native infrastructure. So which means the entire horizontal layer of infrastructure is actually getting used by the classical computers on a cloud native architectures. So when you are deploying these systems, because these are open architectures, a lot of things are also available in open domain. So there's huge amount of security risks that are possible. So one on the device side, so we're getting a variety of it. So previously it was only mobile phone, now we have IoT devices, vehicles, VR headsets, so many things are coming. But on the network side, so if you keep the radio aside, so rest of the infrastructure is all the traditional Intel kind of hardware, so which you can attack with all the cybersecurity scenarios. So this is another huge challenge. So as we build this technology, so we have a bunch of risks that are coming into it, and with the speed that we are creating with the telecom network, we are also increasing the speed of creating these attacks itself. And there are multiple attacks that are possible with 5G and 6G networks. So yeah, so again, how do we navigate here in case of these things? So this is being discussed at standards extensively, and a lot of things are actually corrected. So legacy networks like 2G, 3G, you can actually tap the network and see the messages and also listen to the conversations. These are solved at 4G and 5G. And with 6G, again, AI is getting integrated into the standard, and the QKD, the quantum key distribution, and PQC are also getting integrated into the network. So which means because you have high speed capability, so now you can actually integrate this the PQC algorithms which requires bigger bit rate, bigger bits, and then the QKD is also getting integrated as part of the standardization. So quantum is some way integrating into this 6G network. So that's one of the future network initiative that's going on in 6G. So now again looking back, so combining all these three forces, so we are looking at a world where we have accelerated computing through different methods, accelerated communications, but enough number of risks also are also coming on way, and there are methods that we can work on. So basically, one of the things is, so yeah, there are multiple remediation approaches that are there, but I think it is important to understand the flip side of this technology is also very early, and then adopt strong standardization practices. So with that, I will just conclude the presentation, and thank you for the opportunity.
So thank you, sir, for this talk, which covers all the three aspects of this theme, that is AI, quantum computing, and communication technologies, 5G, 6G. So we'll have questions during the panel discussion. So now we'll go for the panel discussion. Yeah. So the title of the panel is India's Quantum Computing Roadmap, Bridging Research and Implementation. And the panel moderator is Dr. Fani Kumar, from the Scientist E from DST. So he has more than 20 years of experience in academics, research, and scientific program management, and currently working as Scientist E in DST Quantum Mission. He has been mainly focusing on activities related to successful implementation of National Quantum Mission, a flagship initiative by Government of India to drive and develop quantum technologies. He is actively involved in coordinating with thematic hubs to foster developments of quantum technologies, startups, human resource development, and translational research. Prior to DST, he has worked as a scientist in Aryabhatta Research Institute of Observational Sciences. He holds PhD from Osmania University and National Atomic Research Laboratory of ISRO in the area of space physics. During his doctoral period, he was actively involved in various companions related to scientific activities to support PSLVs and GSLVs satellite launches. He has published more than 50 research papers in reputed journals and guided 2 PhDs. He is the recipient of Young Scientist Award by International Union of Radio Science, URSI General Assembly in October 2005. So now I welcome you, sir, to moderate this session, please. We need. So we'll continue without having the tea break. Those who would like to have the tea can have their cups from outside and can bring here. So we'll continue with this.
Thank you, Dr. Sanjay Singh. For the interest of public and also time, actually all the speakers who are already gave lectures will also be a part of panel members. So in this, the session is actually India's computing roadmap, bridging research and implementation. So first I'll introduce each panel member and then they'll no issue. First I'll introduce, no problem. So first is Dr. Tripta Thakur. She is a Director General of National Power Training Institute, an apex body of Ministry of Power, Government of India. She took over the leadership of institute when it is under severe strain due to losses, and she was earlier head and professor of Electrical Engineering Department of National Institute of Technology, MA NIT Bhopal, India. She is a graduate in electrical engineering with master's degree in power electronics from IIT Kanpur and has a PhD from IIT Delhi. She has been recipient of several awards such as Commonwealth Research Scholar at University of Dundee, UK, Commonwealth Academic Fellow at Durham University Business School, etc. She has more than 100 publications to her credit, and she has a research experience of 33 years. She has also been a consultant for evolving a possible common South Asian electricity market. She has done various consultancies for distribution companies in India. She is also a recipient of Women Technology Innovation Award by Indian Smart Grid Forum, STEM Women Award